finish this today's lecture as fast as possible. So we were speaking about 8086 microprocessors. We were speaking about microprocessors. Then we spoke about 8085. Then moved on to 8086. In 8086, with respect to you, there are certain key things which are important. It's just an introduction part. There is basically a requirement of pinout, the architecture diagram, then how your particular 8086 works, the basics of the features of 8086, and that's it. There is no programming requirement as part of the syllabus. So we will focus on the basics of it. We already introduced the pinouts. We had discussed about the signals which are associated with 8086. I have explained almost to a certain extent what each of these signals are, and we had seen the pinout associated, the pins which were being used as part of your HSS. All these things we had seen in the last class. So in today's class, one second, just give me 1 second. Okay, so in today's class, we will basically be dealing mainly with the architecture of your 8086. So, so these were the things which were discussed. So we had also had status signals. So we had around 7 status signals, out of the first 3 status signals, that is S2, S1, S0, was similar to the S1, S0, which was seen in your 8085. It spoke about whether you are having a read operation, write operation, memory operation, an IO access operation, interrupt technology operation, or something related to halt. So it basically gives you the idea about the state in which your microprocessor is. That was your S1 to, S0 to S2. Then we had S4 and S3 here being used for segments. That means which is the segment which is active at this particular moment of time, or which is the segment which is being accessed at this particular moment of time. As I told you, your memory is divided into different segments, similar to the chapters on a book. So you have different kinds of memory depending upon what is getting stored in each of these locations. So accordingly, which kind of memory is getting accessed, according to that, you will have the corresponding values of these particular status signals. That is your S4 and S3. So again, S7 was basically used for your representation of your BHE and certain status signal with respect to your 808. So BHE is your bus high enabled signal, which is used to tell that your data D15 to D8 was having a high state during this particular. So these were the basic signaling setups which are being used as part of your 8086. Now today we will mainly discuss on the architecture of your 8086. So I'll just start off the architecture. So as I told you, the major thing to be noted here is the division of work. You are dividing the work into 2 entities so that you can support the pipelining nature. The architecture is quite simple compared to the simple compared to the architecture which was there for your 8085. But the general thing that you need to notice is it is divided into 2 entities. You have bus interface unit and the execution unit. Bus interface unit is associated with interfacing with your memory, where your execution unit is associated with decoding of your particular execution, instruction, and then executing it. So as you can see, you have 2 kinds. One is the ALU unit. Other than the ALU unit, you are also having a dedicated adder unit, Sigma. Sigma basically represents an adder unit. This is used to create your physical address. We will see that how do you create the physical address and all. And it takes inputs from the different segment registers, which will have addresses of the starting of these segments. Okay, so along with that, it will add your offset addresses, and then the value for the memory interface, the value to be loaded into the instruction scheme queue is generated. So you have an addition which is happening, which is basically used to calculate the physical address from the segment addresses which are available. Okay, so you have different kinds of buses. C bus is control bus, A bus is ALU bus, B bus is another bus which is being used for this, and your A bus is a 16-bit bus, C bus is 20-bit, and it can be extended. It has all the control signals associated with the fetching operation, and B bus again is used as a 16-bit bus to add the value. So this particular adder is a 20-bit adder. So all these three components, that is your 20-bit adder, your segment address values, instruction pointer, and your instruction queue. As you can see, we are supporting pipelining. So you are able to load, it's a byte queue. So each of these in particular locations are in the size of bytes. So 6 bytes of data can be stored, which implies, since it's a 16-bit data line, usually you will have 3 instructions which are stored inside this particular byte. So the loading, I mean the fetching of the instruction will happen parallelly, and you can take out the instruction, execute it, and then move on to the next. When you move on to the next instruction, you will have already downloaded or fetched the instruction for execution earlier. So these two entities will function parallelly, the fetching part and your decoding and execution part. So that's evident from this particular diagram. Then other than these, you have the general purpose registers which are being shown here. You have the ALU unit, you have the control system which is used to control everything. So the decoding and execution will be done by the execution unit. So everything related to that will be there in the execution unit. The operands, the flags, everything associated with that will be there. It's a very simple architecture diagram. It's very easy to remember also. So it's easy to explain also. So there are different 3 buses. Understand that A, B, C buses are there. A is inside your execution. It's not address bus. It's ALU bus. And you have B bus, which is B bus, and C bus, which runs in your BAU. And I think the C bus is it's not only 20. I mean, there's other control signals as well. So size of the bus is not significant here. Okay. So you can mention. I think you will be able to explain each of these blocks in detail when you are asked a question on that. So that's the idea of the architecture of your 8086. Now, we have already explained that. So EU is associated with decoding and execution. BAU is associated with fetching of the instructions. So sending out addresses, fetching instructions, reads and writes, handling of data and address on the buses of EU. So everything related to the fetching part and moving the data from your BAU to EU is done by the bus interface unit. It acts as an interface between your buses and also to your memories. Okay. So it's basically division of labor. Okay, as you can see, the execution unit consists of control circuitry, instruction decoder, ALU, flag registers, and the general purpose registers. So general purpose registers is a combination registers. It's a paired registers. It's a 16-bit register which consists of 2 8-bit registers. So AH and AL. AH is the high ordered value, and AL is the lower order value. So combinedly, they form AH register. So they can be accessed as 8-bit registers or 16-bit registers. It's common for all the 4 registers: A, B, C, and D. Okay. So this is your flag register, which is there inside the execution unit. So you have, other than the usual flag, so it's a 16-bit register. Since it's a 16-bit data bus and 16-bit is the set of values which are going through the 8086, almost every particular addresses or values associated with your 8086 will be 16-bit. So here it's a 16-bit address, and lots of things are undefined. You have the carry flag, you have the parity flag, you have the auxiliary carry flag, the 0 flag, and the sign flag. Everything same as your 8085. So I think this is bitwise compatible with 8085. So it's quite similar to what happens in 8086. Other than that, you have other flags like trap flag for a single step. So you have an option of single stepping the execution to aid the testing part of your 8086. So that is done using the trap flag, which will set up the single stepping process. Then interrupt enable flag is the IF flag. Then DF, direction flag for string instructions. So there are instructions. So here we are speaking about not only the data which comes as numbers, we are also talking about string based instructions which can deal with strings of data, characters of data. So this is basically associated whether the string instruction direction flag for string instruction. That means whether it's going in, from the particular microprocessor or to the microprocessor. So it's something which is related to the string instructions which are supported by your 8086. Overflow flag, if the operation performed by the ALU overflows, then you have this flag being set. So there are additional flags compared to your 8085, but the basic flags will always remain. So whenever you are asked about flags, the 4 flags is always there. Not 4, 5 flags: carry, parity, auxiliary carry, 0, and sign flag. The rest of the flags depends upon the type of microprocessor that you are dealing with. Okay. Now, moving along to the way in which the memory is organized. So inside your bus interface unit, you're having a queue where you will be storing the pipeline. You have a pipeline structure where you'll be storing the addresses which are associated. The instructions which are associated with instructions. So not only one instruction, more than one instruction. That means a possible set of 3 instructions can be stored in a 6-byte instruction queue. Then you have segment registers. If you go back to it, you have a set of segment registers associated with each of the segments, the extra segment, code segment, stack segment, and data segment. Okay, so you have 4 registers associated with the segments in your memory. Then you have your instruction pointer, which points to the instruction currently being executed. So these are the different things which are there inside your particular bus interface unit. So that's the idea of bus interface unit. This is how the memory will look like. As you can see, the whole memory is divided into different segments of equal size, 64K. So you have 1 MB of memory divided into 4 different entities of 64K size, which has a bottom. You have a top of extra segment, the highest address, then this is your extra segment value. Then it starts from 70000h to 7FFFH. The rest is the usual memory. Then you have the stack segment, which is given from 500h to 5FH. This is your top of stack segment. This is the bottom of stack segment. This is the top of code segment, bottom, top, bottom. So these are the different segments, each consisting of 64Ks of data defined in different ranges. So extra segment 7000h to 70000h to 7FF. Similarly, 5 to 5FF, 3 to 3FF will have different values. So each will have a maximum bottom and a top value which is associated with that particular segment. So that is being mentioned here. So this is the physical address, this is the memory, this is the highest address. So inside your particular memory, this is how your particular memory is divided into different segments. Okay, so hopefully this is clear. So you have a continuous set of division from 2000 3000, then there is a gap from 4000 to 5000, then again there is a gap between your 6000 and 7000F, so which can be used for anything. But this is the standard way of dividing your memory into different chapters. Along with it, you have other memory options which are available, which you can use. So this is the standard way of dividing your particular memory in the case of your 8086. So moving along. So how do you calculate the physical address? Now you have different registers, you have different ways of dividing the memory. How do you calculate the physical address? Something which is being explained here of a particular code byte of a particular instruction which is getting executed. So you have the bottom or the starting address of the code segment given in your code segment register. So along with that, you add, so CS, this value, this 348A value is from the code segment register, which will store the base address of your code segment, which is explained here, but this can be changed, changes can be made, but this is a standard way of dividing your memory. But the code segment will have the starting address of your particular code being executed. Along with it, you will add instruction pointer. So both these are 16-bit values. So, but the operation that is performed is a 20-bit addition. So you will add a hardwired 0 at the end of your CS value, then shift your IP instruction pointer to the right, and then add it with it and get the result. So this will be the physical address associated with the execution of a particular instruction. So you will get a physical address by using the code segment and your IP. It's very significant. The other cases, it was the IP address which are giving the direct data, but when it comes to segments, the way in which a particular value is accessed with respect to the N instruction is done using a addition operation. It's a 20-bit addition operation. Code segment will give you a particular data. It will be a 16-bit data. Along with it, you add a hardwired 0. So a 0 will be defaultly added. Along with it, you add your instruction pointer data, which is again a 16-bit data. Shift it towards, the addition is done by shifting it towards right. And then the final result will give you the, or the exact value where your instruction will be there. So this is where the code byte is. So this is the start of the code segment, which is given as 34848AH, and then this is the IP value, which gives you the offset value. This is called as offset value, which will be added with the code segment start of the code segment value, so that you get the corresponding physical address. This is the same in the case of your stack as well. So you will have the start of the stack given here, and you have a stack pointer. So the top of the stack is obtained by adding the stack with stack segment register with the stack pointer. Same operation being performed, same method, but the values here, in the other case it was code segment and IP, and here it's stack segment and stack pointer. So same process is used for different segments. So you will have a segment address and then an offset address. The offset address is added with the segment address using the 20-bit adder, which is provided in your DIU, this interface unit, using adding hardware 0 and right shifting your particular pointer value and getting the value. So that is a usual operation. So for each segments, you will have a segment register and a offset register. So code segment, you have the code segment register and the instruction pointer. Data segment, you have the data segment register and the source index. Extra segment, you have the extra segment register and the destination index. Stack segment, you have the stack segment register, stack pointer, or a base pointer. It is also called as a base pointer. Okay, so these are the different kinds of registers, bar offset registers, which are used to find out the exact address where your required information is stored. So that's the idea. Now, when you consider the programming model of your particular 8086, this is how it looks like. Basically speaks about the registers. Programming model is the model or the values which can be changed. That's your registers. Here, as you can see in BIU, you will have 20-bit you have a 20-bit adder, and you have your extra segment, code segment, stack segment. All these registers are available. Instruction for all these are 16-bit registers. You need to understand that all these are 16-bit registers. We are using maximum 16-bit to store the 20-bit data. So you have seen in the previous slides how do you create the 20-bit value. So that is done using a 20-bit adder, but all these registers are 16-bit registers, and they will have the addresses of different segments and also the instruction pointer. EU registers are basically your general purpose registers, your A, B, C, and D registers. A is called as your accumulator register, B is called as base register, C is count register, D is data register. So this is basically based on the way in which the values are stored. It's a what is a informative statement. So this will act as accumulator. This can be act as a base register. Base-based values will be stored here. Counting values will be stored here. Data values will be stored here. Then other than that, you have stack pointer, base pointer, source index register, and destination index register, which are used to create or which are used to generate your corresponding exact addresses, as we have seen in the previous slide. So this is the programming model of your 8086. It's a very simple programming model which consists of different segments and different registers. Okay. So just a briefing on the instruction set of 8086. Can be 16-bit words or 30-bit, 32-bit double words. Signed numbers, ASCII characters, and BCD numbers are can be operated. So it has 135 basic instructions on individual bits, byte, 16-bit. So it supports bit, byte, 16-bit, and 32-bit. So the data size is usually told as a word. So word size in the case of an 8085 is 8-bit. Word size in the case of 8086 is 16-bit. So, so you have 16-bit words, 32-bit words, signed numbers, ASCII characters, BCD numbers. All these different kinds of operands are supported by your 8086. As you can see, the set has increased, the complexity has increased. Hence, its characteristics, data copy, arithmetic, logic, program transfer, string manipulation, machine of. So you have an additional thing called as string manipulation, which is based on string-based activities. So you have multiply, divide, jump based on multiply, different kinds of instructions which are based on string manipulation, which is not there here. The idea that has to be taken into account, or which you have to understand, is there is complexity involved when it comes to 8086. As you move along to 80286, 386, 486, Pentium, I haven't put a slide for that. Possibly I will send you a slide on that. So there's a comparison which is being mentioned in the syllabus. So you will have complexities increasing. The buses will change, the address buses will change, the number of instructions which are going to be used will change. You will have more blocks inside your particular architecture, more pipelining setups. The pipeline might get increased. So these are the things which happen as you move from the basics of 8086 to 286, 386, 486, and Pentium processor. So that's a basic idea. So I guess that concludes your introductory part on 8086. I kept it as small as possible, as precise as possible. You go through it and try to understand it. So there are certain basic concepts which are being used in even today's microprocessors. Going into the programming in depth. Now, 386, 486, 586, 486, and then Pentium processor. A comparison is required, so you can go through the net to get the comparison statement. I will send you a slide as well for your understanding. It just gives you the values, the number of values related to each of these things. That becomes the comparison between each of these processes. So from next class onwards, we'll move on to 8051. So I will have a recap of the microprocessors and other things. And if you have any doubts based on the topics which have been discussed until now, you can have that discussion in the next class before we move on to 8051. 8051 is the starting point of your microcontrollers, the starting point of Arduino boards, Raspberry boards, whatever boards that you are going to use. So it's a base of most of the things that you will be using as part of your different projects which you will be doing during your engineering career. So try to understand the stuff which is being explained, and then we will see how things will move on. So I guess that's it for today. One second, just don't leave now. Stop recording. I guess. Okay, just want to Neetu Matthews drive, so just share me the details.